Hello everyone and welcome. In this video, we'll be going through the problems from the Junior 2022 second round, which was just held last Saturday on the 25th of June. I'll be going through the solutions to the 5 problems, but more importantly, I'm also going to be discussing what sorts of things to look out for when you encounter such problems, and also certain solutions that don't quite work or at least potentially may lose some marks. So hopefully this will give you a better understanding of how to approach these problems. Now, just as a reminder, the actual competition is a 3-hour paper for these 5 problems, and each problem is worth 10 marks and requires a full solution. Now, what that means is that this video is not 3 hours long. Most of the time you will spend in a competition that lasts 3 hours is going to be time thinking. It's going to be spending time experimenting on things that don't always work, as well as some time writing out your solution as systematically and as straightforwardly to understand as possible. Alright, so let's begin by looking at the first problem, which in a sense is not too difficult. It's not too difficult because this is a problem that doesn't require you to necessarily prove that much. It is more like a round 1 kind of problem, a difficult round 1 kind of problem where you need to be quite careful in how you write down your explanation. Okay. So let n be a 6-digit number. The first 3 digits and the last 3 digits of n form 2 3-digit numbers. So n is a 6-digit number. There are 2 sets of 3 digits. And if you multiply these two together, you're going to get 1/7 of the value of itself. Okay, so the whole thing is going to be n. Let's say that we call this first 3-digit portion A and the last 3-digit portion B. So what we are saying, or rather what the question is saying, is that A times B is 1/7 of n. It's a very, very straightforward statement. Now, perhaps it's a little bit surprising that from here, we are already able to find the value of n. Now, take note that when they say find the value of n, it means that you're not just supposed to give an answer for, okay, I found that n equals to this number or that number. What you're supposed to show is also how is it that no other values of n work. In other words, you're supposed to solve this systematically and arrive at the conclusion of n equals to whatever the answer is. So you cannot just give an answer. If you just give an answer, perhaps you would get something like 2 or 3 out of 10. So that wouldn't be ideal, especially since any one of you who manages to come up with the answer probably already had a systematic way to come out with that answer. It is really difficult to randomly guess this answer, in my opinion. So as long as you already know the method, then just state it clearly. Do not just put the answer down and roughly write down a couple of lines to explain how you got it. That's not quite going to cut it for a round 2 problem. Now, AB equals to 1/7n. One thing we can say is n's a multiple of 7, but that isn't quite that useful. A more useful conclusion is that instead of having 3 variables floating around, we can also say that n equals to 1000a plus b. This is the definition of 2 blocks of 3-digit numbers giving you a 6-digit number. So I can write this equation just in terms of a and b, and I will just multiply the 7 over like this. So 7ab equals to 1000a plus b. Now bear in mind that a and b are 3-digit numbers, so this is going to be fairly large, and it's not going to be very easy if you wanted to do something like guess and check over here. So how then are we going to find out the solutions for a and b and thereby obtain n? There are a couple of methods which are quite closely related in solving these kinds of equations, but I'm just going to show one which I like. and that is to so-called complete the factorization. So we can shift everything over, and obviously this does not yet have a nice factorization. But we are working with integers after all. So we don't mind if we introduce some constants on the right-hand side in order to allow us to factorize the left-hand side. So we can try to factorize. The first two terms have a common factor of a. Now, b, unfortunately, is not going to be 7b minus 1000. And it doesn't even have 7b. So what I can do is to just introduce in an extra factor of 7. And then I will force out 7b minus 1000. Now, of course, this 1000 did not exist, so I will need to compensate the right-hand side with 1000. Now we have a factorization 7a minus 1, 7b minus 1000 equals to, well, 1000. And this is pretty notable because even if we didn't know anything about a and b, this is already quite good because 1000 does have a limited collection of factors. So if there's a limited collection of factors, we could theoretically just check all of them, see which of them give you integer values of a and b. However, we have something more that we can make use of here. We can make use of the fact that a and b are 3-digit numbers. Now, when a and b are 3-digit numbers, it means we don't just know that a and b are positive integers, we know that they are at least 100. And that is quite significant over here because 7a minus 1 is therefore going to be at least, I'll write this on the left side so that I don't mess up my main solution. 7a minus 1 is at least 699. And so the only factor is going to be 1000. Alright, so this is nice. And so effectively, we are concluding that 7a minus 1 equals to 1000 and 7b minus 1000 equals to 1. Both of these give you a and b are 143 and n is 143, 143. So we found that answer. Now let's just try to write this out a little bit more systematically. So what I've done here is almost okay already, but we would just like to add a little bit of details. Because if you just wrote this down, nobody would know what are a and b referring to, and that is going to be not very helpful. So I would like to add in a line to say, let the first 3 digits and last 3 digits of n be a and b respectively. So these are the sort of things that when you're writing a solution, you realize that, hang on a second, nobody knows what a and b mean. If you drew something like this, that's still okay, but it's a little bit informal. So we want to be as neat as we can. The rest of the steps are just algebra, so no problem there. And then after that, we want to say precisely what I wrote on the left-hand side, but in words. So since a is a 3-digit number, a is at least 100. So 7a minus 1 is at least 699. The only factor of 1000 greater than 699 is 1000 itself. Now, if you just say that it must be 1000, sometimes you're going to get away with it. But you want to make sure you explain why, because it may be taken as you're just pretending. You don't know why it must be 1000, but you just guessed it. right? But you're explaining here that, oh, because it can't be that small, so therefore it must be 1,000. So say it with as much detail as you can, not because you're trying to impress the marker, but because that is technically required. Otherwise, you would just need to check every single possible factor of 1,000. Okay, the rest of this is just what I've written on the left. So n equals to 143, 143. And that will be the first problem. Let's move on to the second question, which is a geometry question. And it is not really the most difficult geometry question, especially after you draw the diagram in a reasonably neat fashion. So in triangle ABC, M is the midpoint of AC. Let's try to draw that out. We don't really know how the triangle is going to look, so we just draw any triangle. Roughly don't make it look equilateral, because that's going to confuse you a lot when you keep thinking that stuff are equal to each other or intersecting with each other. So try not to do that. Now, M is the midpoint of AC. The bisector of A meets the side BC at P and MB at N. So the angle bisector meets this at P and N. Suppose the angle A&M is 90 degrees. Uh-oh, that doesn't look very much like 90 degrees, does it? Now, this is not horrible. But if, let's say, you want to adjust it, then you can try to tweak it, either by tweaking the items in your diagram a little bit, or by drawing an entirely new diagram. I think if you try to tweak it, you'll see that this is going to be really weird, because these two angles clearly do not look the same. So we probably would need to draw another diagram out if we hope not to get too confused. So let's try again. But now we understand a bit more about where things should go, so we can draw it in a slightly different order. Now I'm going to draw the bisector first. Okay, so I don't know, actually, at this point, whether I want to put B, let's say here, or maybe I want to put B down here, or maybe I want to put B down here. So I haven't decided that yet. I want to get the important parts down first. So the bisector is already fixed. It should look something like this. I would like BM to be perpendicular to this, so that A and M is 90 degrees. So I'm going to draw something perpendicular first. Something like this is decent enough. And so that means that, all right, this is going to be B. And this is M. This is N. And M is supposed to be the midpoint of C. So C somewhere here. And I'll draw in the triangle at the end. So we can draw things in a different order in order to make sure our diagram looks as neat and as readable as possible. I say readable not because you are going to read a diagram, but if two things are supposed to look equal and they don't look equal, it is really confusing and it's really hard to spot what you're supposed to spot. Now, based on this, CP is supposed to be 2 times of PM. So let me draw in PM as well. And let's look a bit at this diagram. If you've drawn it nicely, and it doesn't need to be perfect, I think what I have here is good enough. You can tell that actually this line AP is sort of a line of symmetry. It's sort of a line of symmetry that reflects B over to M. And that's because of the angle bisector as well as the right angle. Now we can write this a little bit more formally But basically all I'm trying to say is that since these are reflections of each other, you would expect things like, okay, so AB should be equal to AM because it's a reflection. You would expect that BP is equal to PM. So you would expect these to be equal as well. And well, one of them is related to what we have, right? So CP equals to 2 PM. So it means that we need CP equals to 2 times of BP. Now, how are we going to find something like the ratio of CP to BP? In fact, there are a couple of ways this can be done, which are both quite related to each other. One way would be to think of this in terms of area. If we think of this in terms of area, it would be trying to show that the area of APC is 2 times of the area of APB. Or, if you know the angle bisector theorem, then the angle bisector CP equals to 2 times of BP just requires AC to be 2 times of AB. Both of these are then going to converge to the same thing, which is that AB equals to AM equals to MC, because M is the midpoint of AC and we haven't used that yet. So effectively, we have already solved the question, and there are just two things that we need to do. One is to write down all the intuition we have more neatly, and two, we also have to decide which of these we're going to use, which is the one that you prefer to write. And that part is completely up to you. It depends on what you're familiar with and which ones you know how to state properly. One more thing that I have to highlight is that although this is not strictly necessary, it is good practice to start writing your solutions from forward to back. So do not work backwards from CP equals to 2 PM, CP equals to 2 BP, and go all the way back until AB equals to AM equals to MC. This is working backwards from the conclusion, and it is okay assuming that all of your steps are reversible. But it's not good practice because you would like to start from what you know and get to your conclusion. You wouldn't want to start from your conclusion. It's sort of like if you're trying to get from point A to point B and you wanted instructions, you wouldn't want someone to tell you how to go backwards from point B to point A. You could reverse the steps, but you don't like it very much. Alright, so all that being said, let's start off with showing that this is actually a reflection. So to show that this is a reflection, we can just say that triangle ABN is congruent to triangle AMN. This is true because we have a couple of angles and a common length. So by ASA congruency, which is BN equals to MAN, BNA equals to MNA equals to 90, and the common side AN. So remember that we want to get BP equals to PM. That's what we need. So in order to get BP equals to PM, what we need is to have triangle ABP and triangle AMP to be reflections. In other words, that's the congruent triangle we want. So I'll mention that AB equals to AM. And so this in turn implies the other congruent triangle that we want, ABP and AMP. This one is going to be by side angle side congruency. So AP equals to AP, AB equals to AM, and angle BAP was angle MAP. So this was what we want, BP equals to PM. Now, I'll use the angle bisector theorem as well. And in order to use the angle bisector theorem, I will also just add on top AB equals to AM equals to MC. That is from the fact that M is already the midpoint. So, by the angle bisector theorem, BP to CP. I'll write it the other way. CP over BP is equal to AC over AB, and AC is 2 times of AB. So finally, we want to replace BP by PM. For CP over PM equals to 2, and CP equals to 2 times of PM. So that's your solution. You could have written it using area as well, but pretty much all of it centers around just noticing this reflection. As a general comment, the questions for SMO Junior Geometry don't require anything too sophisticated. So you would always be looking for things like area, congruent triangles, similar triangles, and Pythagoras theorem. The very basic stuff can get you quite some distance. Angle bisector theorem here is optional, but I think it does help us to shorten the explanation just a touch. On to question 3. Let n equals to P1, P2 to Pk be the product of distinct primes P1, P2 until Pk, where k is greater than 1. Find all possible values of n if it is a multiple of Pi minus 1 for each I equals to 1 to k. It seems to be a little bit abstract. So we need to probably understand a little bit of what's going on. So for example, k is greater than 1. So you need to have at least 2 primes. So let's try. If k equals to 2, and let's say my 2 primes are pq. I think I'll just use P1 and P2 to avoid any confusion. You can change the name in your experimentation. So n is the product, and we need it to be a multiple of P1 minus 1 and P2 minus 1. Now this one is a little bit iffy. If you just try to experiment, you realize that already is quite difficult to do. And one of the reasons why this is quite difficult to do is simply that P1 minus 1, P2 minus 1, you would expect there to be an even number. If you try, let's say P1 is 5 and P2 is 7. So this would be 4 and 6, but 5 times 7 is 35. It's clearly not going to be a multiple of 4 or 6. So you know that you are definitely going to need something to be even. So one is even, possibly both, but they definitely can't both be odd because only one of them can be equal to 2. So at least one is even, and that implies that you need one of them to be 2. Well, we can assume that P1 is smaller. And so we assume P1 is smaller, it means that P1 should be equal to 2. And now, this becomes a multiple of 1. So that's obviously true. The other statement we need is 2P2 is a multiple of P2 minus 1. Well, this is not very difficult to do, and you can deduce it in a couple of different ways. But I think the easiest way to think of this is that P2 minus 1 is definitely not going to have any common factor with P2. So that prime number is not going to help because this is smaller. So if your prime number, let's say, is 17 and this is 16, well, it's smaller than the prime number. So the prime number is not contributing. So effectively, there is only 2 that is going to be a contributing number, contributing factor. And so P2 minus 1 has to be equal to 2. So this is the only solution, and it gives n equals to 6. Now, let's say that we try out something after that for k equals to 3. So by the same logic, we can do similar steps. We write down that, let's assume that these are in order. We assume that P1, P2, P3, one of them must be even. So we can take that as 2. And we're left with 2 P2, P3 is a multiple of P2 minus 1 and P3 minus 1. Now, if we look at this here, and let's try to use the same logic again. Firstly, P2 minus 1. How am I going to satisfy the factors of P2 minus 1? Certainly, it's not going to come from P2. It is also not going to come from P3 because that's even larger. So for example, if let's say P2 were 7, and I'm looking for a multiple of 6, P3 is just going to be really big prime numbers like 13, 17, 19. Now that's never going to have anything to do with a multiple of 6 because it's a prime number. So this is also not going to contribute anything. And just like before, we're going to get P2 minus 1 is equal to 2 again, and P2 is still equal to 3. So let's say that we now have P2 is 3, we have 6P3 is a multiple of P3 minus 1. By the same logic, P3 is not going to be contributing anything to P3 minus 1. So P3 minus 1 has to be a factor of 6. But it can't repeat. So the only possible one is that P3 minus 1 is 6. And P3 is equal to 7. Well, this gives you n equals to 42. Let's go on and put in another prime factor, and you probably have a decent idea of what's going on by now. The first one must be 2, that is clear. The second one, if I put in P4 again, it doesn't do anything because that's still not going to contribute, so this is still 3. And likewise, this is still 7. So the pattern effectively continues. We just have to look at P4 to find out what it is, and hopefully we get some idea of how much further I need to look, because this is going to be pretty frustrating if I have to go and keep multiplying more and more and more prime numbers. So hopefully it stops after a while. So 42P3, sorry, 42P4 is a multiple of P4 minus 1. Again, P4 is not contributing, so P4 minus 1 has to be a factor of 42, and it has to be an even factor of 42. So, because P4 should be odd, so we're looking for even factors, and the even factors you have are 2, 2 times 3, 2 times 7, and 2 times 3 times 7. Now, all of these, you get 3 and 7, which are already used, 15, which is not prime, and 43, which is actually going to be possible. So we do get P4 can be 43, but it also only can be 43. And we have to repeat this one more time. For k equals to 5, you can probably guess what's going to happen. Repeat the same argument. 42 times 43 is 1806. It's going to be a multiple of P5 minus 1, and then we take even factors again, and we see, right? 1806 is 2 times 3 times 7 times 43. That's, of course, what we already know P1 to P4 have to be. So we just look at their even factors, and it is going to be just the same group except that we can multiply 43 in. So times 43 times 43 times 43, and yeah, we get all of these values. Sorry, not the arrow there yet. And if you check whether any of these plus 1 gives you a valid value of P5, the bad, or rather the good news, is that none of them work. And none of them work because if you just focus on those below, you get 87. The ones on top I already used up. So 87 is 3 times 29. If you take 259, this is 7 times 47. If you take this 603, it is a multiple of 3. And if you take 1807, it is a multiple of 13. So that's great news because it means that you cannot find P5, and so that's it. And that's it. And by that, we mean that we have confirmed that n equals to 6, n equals to 42, and I think I should have said that n equals to 1806 are indeed the only possible solutions. I'm going to take a bit of time to just show how you can write this out systematically, because we have all the things we need, but you need to express it in words, and sometimes that is also its own challenge. But if you already think you know, feel free to just skip this part and look at question 4. Now, first things first, if we are looking at an argument like this, k equals to 2, 3, 4, 5, and so on, sometimes it is useful to just mention the answers first so that the person reading it can anticipate how many different answers they are going to see. So this is for the benefit of the reader. We can do that. So we claim n equals to 2 times 3 equals to 6. 2 times 3 times 7 is 42. And n equals to 2, 3, 7, 43, and it's 0, 6 are the only solutions. Now, writing something like this is a courtesy because for someone who's reading it, it sort of prepares them that, okay, in your solution, you're going to explain how you came up with these 3 numbers, and also you're going to explain to me why is it that these are the only solutions. Nothing else is going to show up. Now, I don't want to split into k equals to 2, 3, 4, 5 necessarily just that way, because it is a little bit of repetition, right? We are repeating the same logic of the first one has to be 2, the next one has to be 3. And so I'm not going to split it exactly like this. I am going to just split it by if we have at least 2, if we have at least 3, if we have at least 4, and maybe that will be able to save us some writing. So the first thing that we assume throughout is that the primes are in increasing order. So I'm going to just write this here. WLOG is short for without loss of generality. So it means that we can assume this, it doesn't matter since they are just different primes. So why not assume they are in the increasing order from P1 to Pk. Now I want to say first of all that the first one must be 2. Right. So we know, so rather we are given k is at least 2. K is at least 2, and when you are looking at k is at least 2, it means that at least you have 2 prime numbers to work with. So among P1 minus 1 and P2 minus 1, one of them must be even. At least one of them must be even. So since the n is a multiple of this, n must be even. So one of its prime factors is 2. Of its prime factors is 2. And we define P1 to be the smallest. So it means P1 is equal to 2. Now I want to also make use of this logic about crossing out irrelevant stuff as many times as I possibly can. So I'm going to write this down in general as a kind of an observation. And we can do something like this. Just highlight an observation and make it clear that this is an observation that we'll keep on using, or if you want to call it a lemma, you want to call it a statement, you want to call it a claim, up to you. Just sort of make it stand out from everything else, because this is the main idea. The observation is that since pi minus 1, so any of these multiples of pi minus 1, we're trying to use the same explanation. Pi minus 1 is co-prime, meaning no common factor, to pi plus 1 all the way to pk, and these are prime numbers larger than pi minus 1. That's the reason. So since pi minus 1 is co-prime to these, pi minus 1 dividing n means that pi minus 1 is used proper tenses. Pi minus 1 divides n implies that pi minus 1 divides one of the, well, sum or one of the earlier factors, p1, p2 to pi minus 1. So this is the same observation that we used over and over again, that we can now just lump together and just keep on referring back to this observation. So we don't need to explain ourselves so many times. So now we can say using the observation repeatedly. What are we doing repeatedly? We are going to keep on doing this for the next prime, the next prime, the next prime, and so on. So what's the next prime? For I equals to 2, P2 minus 1 divides P1, which is 2. So that means that clearly P2 equals to 3. Now we say that we can stop here and it would work. So if k equals to 2, we do get n equals to 6. Well, so if k is at least 3, so if we have something else, then I guess I can just bullet point it as well. Sorry. For k greater than or equals to 3, I will use this same observation. Now, p3 minus 1 divides p1, p2 equals to 6. And the only possible factor is going to be 6. So only p3 minus 1 equals to 6 and p3 equals to 7 works. So if k equals to 3, we get n equals to 2 times 3 times 7 equals to 42. Then we repeat this again. Now we've already solved this essentially, so we know it's going to stop. Now when you're reading the solution in the solution book, you sometimes wonder, how did they know that it is going to stop? And the answer is they did not. When you were solving it, that's one thing. When you're writing the solution, you don't need to actually explain how did they know that you will stop at 1806 so magically. Well, you will get there. So the solution is written forwards, even though sometimes when we solve it backwards. Okay, so we know that we're almost done. So this is just a little bit of a chore maybe, but do it carefully, especially if you've already solved the question. So this is 42. And so we can mention what we did on top, which is only P4 minus 1 equals to 42 gives a prime P4 equals to 43, prime number. Okay, so likewise again, write down that last number, 23743 is 1806. And then finally, we know that for k greater than or equals to 5, there's going to be nothing already, so just the last bit to write. So we can just say checking directly because 1806 has a limited number of factors. So normally if you write down in a solution and you just say none of the factors of 1806 gives P5, makes P5 a prime larger than 43. So there are no such solutions. Or no such values of n. And we're done, right? Because we have now done 2, 3, 4 and shelved everything after that. So therefore, just to conclude again, I'll give some indication that you have concluded. It's just, again, a courtesy. So the only values of n are 6, 42, and 1806. There we go. Now on to the last couple of questions, which are actually the ones that are, I think, significantly more difficult than the first three. Significantly more difficult because, let's say for question 3, it is not obvious at first glance, but if you give yourself, let's say, 20 minutes of time to just experiment with different numbers and play around with it, you do get a decent sense of how things go. For question 4, you don't really have any straightforward way to experiment and instantly say, okay, I just noticed that this works, this does not work, this works, this does not work. They ask you to prove that it always is true. And also for question 5, if you experimented, it is still less obvious how to get the numerical answer. So these two are a little bit more difficult than the first 3. So question 4, let n be a positive integer. Prove that n squared root 19 times the fractional part of n squared root 19 is greater than 1. The fractional part means that you subtract off the integer part, which is the floor. We still can experiment a little bit in order to see how things go. Right? So in the SMO, you have enough time to do some experimentation. And if you take 43 squared, and I write it as 4.3 squared is 18.49, 4.4 squared is 19.36. So square root of 19 is somewhere between 4.3 and 4.4. Additionally, if we want to sharpen it a little bit, we can say that 13 over 3 is is less than square root 19. So you can estimate it to some decent degree. Remember, there's no calculators in the SMO. But we know that this is true because 13 is less than the square root of 171. So this is true. And we can now, I guess, sharpen it a little bit to 13 over 3 less than 19 less than 4.4. Why I'm doing this estimation is quite simple. I'm going to have to deal with fractional parts. So if I want to experiment, I would like to know what's the integer part that I subtracted away, so that I get a decent estimate of where I'm going with things. Okay, so let's say that we have n equals to 1. It would be square root 19 times the fractional part of square root 19. We can't really write down the fractional part exactly, but we can say that it is going to be square root 19 minus 4. Okay, it's 4 point something. So square root 19 minus 4. And this is going to be pretty far away from 1. Okay? Because square root 19, if we just estimate it, it's about 4.3 times 0.3. It is going to already be more than 1. Okay, so let's see if it gets looser or tighter. If n equals to 2, your left hand side is now 2 square root 19 times the fractional part of 2 square root 19. Now that is going to be somewhere about 0.7. So it's just going to have doubled. So this is definitely much bigger than 1. It's going to be 5 or 6. The interesting part comes when we do n equals to 3. When n equals to 3, the left hand side is going to be equal to 3 square root 19 times the fractional part of 3 square root 19. And if we just did an estimate of saying that this is about 3 square root 19 is slightly more than 13, and then this here is going to be 3 square root 19 minus 13. Well, this is going to be a bit of a problem, right? Because how small exactly is this? And if let's say that we forget the estimate, we want to do it exactly, kind of like what I wrote down here. So we know that the subtraction is 13. So give me 9 square root 19 minus, 9 times 19, which is 171, minus 39 square root 19. This is a fairly bothersome kind of thing because it is actually going to be very tight. How do we know that it is very tight? Well, we can ask whether this is more than 1. It should be. And if you actually did the computation, right, just to show how this is really close. 39 squared times 19, and I kid you not, is 28,899. Which is very annoying. It's very annoying because this tells you that, well, this was really well chosen, isn't it? So it's not just 19 was just a random number. It's not that the SMO had some question left over from 2019, so they put it down here. The number does actually matter. The number matters because if, let's say, you put something like a square root of 17, it doesn't even work for n equals to 1. It doesn't work because this would be, let's say, about 4.1 times 0.1, and this is going to be less than 1. So, in fact, this equation with the value 19 is very specially chosen. So that's the takeaway from our experimentation, right? You might wonder to yourself, Does 19 actually matter, or did it just throw in some random square root? So fortunately or unfortunately, 19 does matter. So first conclusion, 19 matters. The second conclusion is that this is quite tight. By quite tight means that we cannot use very rough estimations, right? So the bound is quite tight. In fact, if you had a calculator and you check this, this is about 1.003. That's how tight it is. So you cannot say, oh, never mind, this is just square root 19, it's around 4. If you did anything like that, it's going to go underneath 1. So based on this understanding, you know that you need to be quite careful. Now, there's also the temptation to say, all right, can I do some sort of inequalities directly on this thing to see what works? And we can try. I write it as the fractional part being the value minus its floor. And you want to say that this is more than 1. Now, unfortunately, you can't really do anything with this. In order to show that it's bigger than 1, you need to make something smaller and still be greater than 1. And if you want to make this thing smaller, the floor function is already smaller. Right? So unless you decide that you want to say that, well, this is greater than 19n squared minus the floor of n square root 19 squared, which is a little bit, I would say, too loose. It doesn't even work if you're doing it for n equals to 3. Because for n equals to 3, this thing here would just have given you 0. So it is quite tight. And a lot of these kinds of rough estimations are not quite going to cut it. Sorry for the slight lag. Let me just check a couple of things. Okay. So since n equals to 3 is this type, we need to do a little bit more of a sophisticated argument. And usually for such things, we can try to do it more algebraically, and I'll write it as a proof by contradiction. We'll see what happens, but we'll write it as a proof by contradiction. So suppose by contradiction that this is less than or equal to 1. Now I'm going to substitute away the 19 first, just so that I can see if I am able to rearrange this into something a bit more concrete. And the square root 19 is just a bit of a nuisance when I'm trying to understand my equation a bit better. So let x equals n square root 19. And now I'm going to just work with x times the fractional part of x is less than or equal to 1. Now, x times the fractional part of x is less than or equals to 1 happens if the fractional part of x is less than or equal to 1 over x, which is quite small, because remember that x is going to be n times square root 19. So if n is even something like 10, you're talking about x being 40 something. So I want to find out, is there any problem with the fractional part being very close to 1? Well, in order to do the fractional part, I think it's easier to work with the number itself. So I'm going to just, so between 0 and this, I'm going to add the floor of x. And I want to ask, well, can x, which is n square root 19, be that close to something like a multiple of square root 19? Right? A multiple of square root 19 be close to an integer. Well, the main thing about x is that it is n square root 19. So why can't it be so close to an integer? You sort of want to square it. Right? So if you square it, you're going to get something like this. X squared is going to be 19n squared. And what happens is that you can say this is telling me that 19n squared is supposed to be quite close to an integer squared, just a little bit more. Right? This is an integer squared. And this portion here, we know that this is going to be less than 2. We know that this is going to be less than 1. So this portion here is less than 3. So if we did this, we're going to get floor of x squared less than or equals to 19n squared less than or equals to floor of x squared plus 2. Remember that we would like a contradiction here. So my question now is there anything contradictory about this? Is it contradictory that my 19n squared can be either just equal to a square number or just slightly more than a square number? Fortunately, we can keep on going back to our n equals to 3 example. And our n equals to 3 example tells us that no, there is nothing contradictory about this. Because if n equals to 3 and this floor of x here is 13, which is indeed what it's supposed to be, then it is actually 171 equals to 171. So there is no contradiction if we wrote it like that. Now you might then say that, wait, did we just show that n equals to 3 is a counter example? The answer is no, we did not, because we have already loosened things a little bit when we changed this to 2. But the problem is that it is very difficult to establish that this thing is going to be less than 2, because it isn't always less than 2. It depends on the value of x. If x is very big, this thing is actually going to be around 2. So now we have a headache because there's no contradiction here. But whenever we have a good idea, we don't want to abandon it. We don't want to abandon it just because it doesn't work, because this is already quite restrictive in the sense that 19n squared cannot be a square. So one of the cases we can eliminate. Now 19n squared also cannot be a square plus 1. Now this one's a little bit more subtle. Because the reason is you need to use a little bit of modular arithmetic. You need to say that a square number plus 1 cannot be 19n squared, because if we consider something like modulo 4, it would not work. So 19n squared equals to x squared plus 1. If we consider mod 4, it tells me that, and I just rearrange this a bit, 3 equals to x squared plus n squared, which is not possible since squares are supposed to be only, it's not the same. I mean, technically it's floor of x, right? I want to say that, but yeah, either way, doesn't matter. Floor of x is still an integer. This is not going to be 3 mod 4 because squares are only 0 or 1 mod. So that does not work. And since that does not work, the only problem is the square plus 2 case. So we have actually almost solved the question, and we have almost solved the question. Don't abandon it, just rejig it a little bit. And so what I would do here is to say that if all this is saying is that x and the floor of x are at most 1 over x apart, I'm going to make floor of x the subject instead. This one tells me that floor of x is greater than or equal to x minus 1 over x. And then this one tells me that this is greater than or equals to x. Right, I'm going to just flip this around because it looks a bit weird to suddenly switch the direction. But it means that I can change it to look like this. I know this doesn't look like much. Seems to be just shifting that chest. What have we actually done? But there is a subtle difference when we square it. Now, this one on the left, we are all quite familiar with x minus 1 over x if you have done some round 1 problems. It's x squared minus 2. The 2 shows up again. Plus 1 over x squared. Now, this is very, very different from what we got because here it was plus and plus. Here it is minus and plus. So it means that we are much closer when we do something like this. We know that x squared is an integer. So therefore, it means that since this x squared minus 2 plus 1 over x squared is strictly greater than x squared minus 2, the only possibilities we have are floor of x squared equals to x squared or floor of x squared equals to x squared minus 1. And those are basically these two cases that we have already resolved. So I can just say the reasons why they don't work. The first one doesn't work. So this fails. Since if it were true, floor of x equals to x is only true when x is an integer. And that is not true because square root of 19 is irrational. And for the other one, we are going to take mod 4. So floor of x squared equals 19n squared minus 1 means that floor of x squared plus n squared is congruent to 3 mod 4, which is not possible. Right? Not possible since all your squares are 0 or 1 mod 4. And if you add up 0 and 1, you can either get 0, 1 or 2, but you cannot get 3. Okay, and remember that when you conclude your solution, we said suppose by contradiction. So tell them contradictions. This is a way of saying that we have done the proof by contradiction, and so hence it is going to be greater than 1. There we go. Not an easy proof, but you do have a chance of recovery if, like me, you started off by writing this down and squaring it and seeming to stumble in the wrong direction. You can switch the direction and do it again. And this is usually the case when you have a solution that seems to work 80% of the time or 90% of the time. There's a good chance that just by tweaking 1 or 2 corners of it, you can make it work 100% of the time. And so don't try to cheat. Don't try to pretend that, well, it can't be 2. try to come up with a proper reason why. You know there is a reason why somewhere. Look for it. Finally, question 5, which I have to say is not easy, and starting with the fact that the question could have been perhaps worded a little bit more clearly. It says, let n be an integer greater than 6, such that if the integers 6, 7, 8 until n are divided into two groups, one of the groups contains the numbers a, b, c with a, b equals to c, where a equals to b is allowed. Determine the smallest possible value of n. Now, admittedly, if you take a plain reading of this, it's just saying that if n is more than 6 and you divide it into groups, one of the groups you have two numbers multiplied to the third number. The two numbers might be repeated. How small can n go? Well, I mean, it does look like it's saying that why can't I just say that I put 6 and 36 in the same place and just put everything else in the other side? Doesn't that already work and give me n equals to 36? This is the last question of the SMO. We know that the last question isn't always the most difficult question. However, it most certainly should not be that easy. So if you're taking it, this is the time where you want to raise your hand and say, I don't get this. Do you mean to say that one of the groups contains it or one of the groups must contain it? Now, that's different. And almost certainly they're going to issue a correction that says one of the groups must contain. So the question is basically asking you, how small is it that you can guarantee such a thing can be found? If n equals to 36, it doesn't guarantee, right? It just makes it possible. But how would you guarantee? This then becomes something that you can experiment with. It's a more difficult experiment than the Q3 experiment, but still, it is something that you can experiment with. Now, your experiment is to try to put in as many numbers as possible without this happening. So here's what you should do when you're trying to experiment, right? During your experiment, you want to look for some trivial bound on n. By trivial bound, what exactly do I mean by a trivial bound? A trivial bound means that you want to find out, even if it's just a very, very lousy estimate, you want to say, for example, why can't n be 100 million and this thing still doesn't happen? Now, that sounds absurd. But how do we know that there is actually some point at which this thing is bound to happen? So why must this happen for enormous n? So in the example I said 100 million or 1 trillion or whatever it is. How do we even know that this is going to happen? Now I know that it's tempting to say, well, if it's so huge, then surely it must happen. From our experience in math, we know that so huge isn't a reason in and of itself. For example, pi. You might say that surely the digits of pi, it must be recurring after a while if there are so many digits, it's infinitely long. But no, it is irrational, so it doesn't ever start becoming periodic. So for things like this, right, why must this happen? Well, I want to answer this by looking at some numbers that are being forced into place. Right, so let's say that I have these two groups. I'll just draw it as two boxes like that. Now, I put 6 here. Now, what at this point is forced if I don't want it to happen? So, don't want ABC to be possible. Now, the only thing that we can say is that 36 must go on the other side. Right? Now, after this, what can we say? Now, we can't say something about 6 times 36 because, well, it's not there. 6 times 36, 6 and 36 are in two different sides. So 216 could theoretically come here, and 216 could theoretically come here. Both of them seem to be possible. Now, the only other thing that is forced is that if 36 is here, and 6 squared is that, then the square of that, which is 1296, cannot be in the same box, the same group. So 1296, which is here, in the first group. Now, I've got two different numbers in the same group, so I can use my combination here. 6 times 6 to the power of 4, which is 6 to the power of 5, shouldn't be in that same group. So 6 to the power of 5 should be in this group. But I also can use division. I can say that 6 to the power of 4 divided by 6. So 6 cubed should also not be in here. But then wait a second. We have then found 6 squared, 6 cubed, and 6 to the power of 5. We have found it inside the same group. So that means if n is 6 to the power of 5, right? Okay, this is not that enormous. It's 7776. If n is equal to 7776, these 5 numbers alone are going to guarantee that one of the groups must contain ABC like this. Right, so n equals to 7776 is enough. Now, once you have n equals to 776 is enough, nobody said that's the answer. What we want to come to next is to think about if I don't have 7776. So this is like my first guess. If I don't have 7776, is anything else going to go wrong? So let's say if n equals to 7775, right? And I still don't want ABC. So I don't want this thing to happen. Now the same logic is still going to apply, right? Which is that except for the 6 to the power of 5, the other things are still going to follow. So you are still going to have a 6 will be here, 6 squared will be here, 6 to the power of 4 will be here, and 6 cubed will be here. And this is still going to be there. Now what I would like to do here is to use a so-called greedy algorithm. Now the greedy algorithm is very simple. Across all problems, the meaning of greedy doesn't actually have the same exact context, but it is still just saying, just fill up as much of one as you can, and then once you cannot fill up the other one, once you cannot fill back the first one, and so on, right? So you just want to stuff in as much as we can. Just go through your numbers in sequence, and as long as you can keep putting them in the same group, just chunk them to the same group. We'll see whether this works. Now, so for 6, I'm going to just keep on putting them all the way until 35. Right now, 6 squared, I cannot put, but all the way from 6 to 35, none of them are going to multiply to each other, right? Because 6 times 6 is already 36. Everything among these numbers, when you multiply them, is going to be between 36 and 1225. Then for the next few numbers, so here, this is going to give me all kinds of products on 36 to 1225, which is slightly less than 6 to the power of 4, because that's 35 squared versus 36 squared. I have a lot of numbers that I need to avoid putting in this group now. So I can't put, let's say, 42, I can't put 49, I can't put 48. I have to avoid a lot of numbers. Never mind, I can just put them all on the other side. So I'm now going to just put, let's say, 37, 38, all the way to 6 cubed. All the way until 6 cubed. Actually, there's no issue here, right? Because when you multiply 6 squared by itself, you're going to get 6 to the power of 4. So everything in this group is going to never ever have a product below 6 to the power of 4. So if my greedy algorithm continues, I can just stubbornly keep on putting in 217, 218, and carry on all the way until 6 to the power of 4 minus 1, which is 1295. Okay, now back to the first group again, because I can't put in 6 to the power of 4. We know that, once again, if we take these numbers and multiply them among themselves, you're going to get pretty much everything from 6 to the power of 4 to something slightly less than 6 to the power of 8, because this is almost 6 to the power of 4. So almost everything else is going to be in trouble because you can get many of those numbers. Forget prime numbers, but most of those numbers that are composite, you can write it like this. So I'm just going to keep on putting all of them in the first group again. Now, interestingly enough, there doesn't seem to be anything wrong down here. There doesn't seem to be anything wrong down here because if you multiply the small numbers among themselves, you're never going to reach the bottom row. If you multiply a small number with a large number, you already get 6 times 6 to the power of 4 is 6 to the power of 5. Now, that was the problem earlier on, but we don't have a 6 to the power of 5 down here. And if we multiply two of the big numbers, that's going to be really huge. So that's okay. Which means that for n equals to 7775, it is okay. It is okay. We have found an example where there are no ABC. So this practically is the entire solution already. All we need to do is just to translate it. So we just need to translate it into the format of a proper proof. Again, if you think you've understood this already, feel free to just pop out here or just to quickly fast forward through this section. But if you want to see how it's written, because this is just a bunch of boxes, it's not that bad really. Just remember that you need to cover it from both sides. So solution, we claim that n equals to 6 to the power of 5, which is 7776, is the smallest possible value. And then we have to just give both of these. One direction is we have to show that for 7776, there will definitely be such ABC. Okay, so I'll just write down, call the groups A and B. So I don't need to draw the boxes anymore. And suppose that no such ABC exists. So we want to get a contradiction. Well, so just follow the same logic. Without loss of generality, let 6 be in A. Okay, then 6 squared, which is 36, must be in B. And then 6 squared squared, which is 6 to the 4, must be in A. So 6 and 6 to the power of 4 are both in A. Means that, well, just see the thing we said earlier on, 6 times 6 to the 4, which is 6 to the 5, and 6 to the 4 over 6, which is 6 cubed, must be in B. But then we get 6 squared, 6 cubed, and 6 to the 5 in B, which is a contradiction. So this is to say that 7776 is enough. the other side of it is to show that if n is at most 7775, then there is a way to put them in groups without this happening. So we now show a way to place the numbers from 6 to 6 to the 5 minus 1 without any such ABC. And we just give the description. So in group A, we have all the small numbers and the big numbers. 6 to 35 and 6 to the 4 to 6 to the power 5 minus 1. And for group B, we have 6 squared all the way to 6 to the 4 minus 1. We need to explain why is it that this doesn't actually have any such ABC, but that is quite simple. Right, so for group B, which is the most straightforward, any two numbers multiply to at least 6 to the 4. Which is not in B. And then for group A, if we take two of the small numbers and multiply them together, we are saying that it falls into the gap. Then 6 squared is less than or equals to AB less than, which is strictly less than 6 to the 4. So AB is not in group A. Otherwise, if one of the numbers is at least 6 to the 4, then AB is at least 6 to the power 5. It's also not in A. Yeah, so you have explained it. And the point is that you don't need to explain how you came out with the construction. So as much as I'm talking about details, remember that for these kinds of problems, you don't need to give the reason for this is how I discovered it. You only need to explain why you are correct. So you don't need to say that, okay, we use the greedy algorithm. Well, that's how you figured it out, but you don't need to write that down. If you write it down, you don't get penalized, but I'm just trying to say that you can save a bit of writing by explaining why it works and not necessarily explaining how you came up with the idea. I hope this was useful. This is quite an interesting paper, I would say. Unfortunately, I think I've heard that some of the participants have seen one or more of the last two questions before. This can't really be helped when we are doing SMO, when we're doing any Olympiads. There are lots of questions that could theoretically have been found in some other place, in some other country or in some other year. So that's part of the nature of it. But the good thing is that whether you've seen it or not, it is possible to reason these things out. Probably question 4 is the most difficult to reason out, but for the rest of these, it is still at least possible. So thanks to all of you for watching. If you have any comments or any questions, please leave them below. Don't forget to subscribe and do keep a lookout for review videos for the senior and open sections coming up in the next few weeks. Thanks everyone, and see you again soon.